Was it too confusing, or was it that Einstein was a Jew? Yeah, it was this Jewish science, right? So he actually had his scientists trying to disprove it to prove a point, which that didn't work so well for him, right? Here's some pictures of gravitational lensing. Just look at this guy right here. This is a distant quasar. That's a huge black hole, a very massive object, right? Do you see these galaxies here that are smeared out like that? Okay, those are actually maybe behind this quasar, but their light is actually smeared around the sun, because that's what it does, or around this quasar there, right? Here's another one, a galaxy here that's been kind of pushed away. I've got better pictures, but there it is. Here, this is the famous Einstein Cross. This is one galaxy, right? It's been pushed away from it. It's actually behind it, but it's been pushed to one side. Here is the Einstein Cross. Why it's 4, I don't know. I don't know why it's 4. Okay, it's 4. Yeah, I'm not a general relative. It involves 4-dimensional space-time. Here's another Einstein Cross. So this is one galaxy behind a nearer galaxy, and we're seeing it 4 times because I don't know why. Okay, but it's the light is bending around that thing, and we're seeing it like that, right? Sometimes it's 2. Why is it 2 and 4? I don't know. In fact, I asked some guy. There was some guy at PSU that was like a PhD theoretical physicist, right? And I go, okay, why the 4? And he goes, I never studied general relativity, and very few people understand it, right? Because it's really pretty difficult stuff, right? So I was at least heartened that I was not alone in my ignorance, that somebody else with a better degree, right, didn't understand it as well. So now we've got this problem, right? It turns out that one of the things that general relativity says is that it's not light that changes its path, it's actually space itself that's curved. And now we're running into this conceptual problem, right? And I think I developed this idea, right? Didn't we talk about, when we talked about gravitational models, didn't we have this idea where I filled the room with water and we put a rubber sheet on the room? Did we talk about that? Right? And then I think I bent your mind with the notion that if we have a one-dimensional universe, we can curve it. This is a one-dimensional universe. We can curve it in ways so that if you go in a straight line, you end up back where you started. Did we talk about that? Yeah, and then if you had a two-dimensional space, right? If you had a two-dimensional space, ouch, okay, that you could curve a two-dimensional surface. Isn't the surface of a globe two-dimensional? Yeah. You could curve it in such a way that if you tried to go straight, you'd end up back where you started. That the curvature of space makes you go in a circle, right? And then we developed the idea of orbit. That's what he's talking about, right? Okay, is that space itself is curved, and this is just really bizarre, right? So you could, if on the surface of a globe, I could draw a triangle with more than 180 degrees. Here's one with 270 degrees of interior angle, right? So Euclidean geometry says that it's got to add up to 180, but here's one that adds up to 270. It's not that they all add up to 270. It's that it could be more, and in general, it's more, right? What if so what we did here, by the way, was we went across the equator, straight up to the North Pole, took a right turn down to the equator. That's, yeah? If that cuts what is that, an eighth of the globe out of there, ooh, a piece of pie, right? I'm going to eat it, right? If you pull that thing out, then that's going to be 270 degrees right there. But in general, it's more than 180, right? This is called positive curvature, okay? And there is a way to actually get less than that, right? Now, what if the sphere are large enough? What if we draw a small enough triangle, or we had a big enough sphere? What if I draw a triangle in Tualatin? Is the curvature of the Earth going to affect it much? No, not so much, but at some point, by the way, maps, they screw up, right? If you draw a big enough triangle, the curvature of the Earth makes the angles not work out, right? Okay. So this is the idea with a black hole, is that if you have a black hole, the thing has so much gravitational field, not because it's heavy, but just because it's small, okay? It has so much gravitational field that the escape velocity is faster than the speed of light, right? So that's what makes it a black hole, is that it collapses inside something called the event horizon. And the radius of this is called the Schwarzschild Radius, okay? Okay? And we can make a formula for this. Basically, we have some object with kinetic energy, 1/2 mv squared, right? And then it's got to have enough energy to escape. Take a football. if it's got to have enough energy to, it's got to have enough energy to escape. This is the energy to escape from a gravitational field, and then we can just cancel the m's there, and we can end up with our Schwarzschild radius, which I believe is 2gm. And don't you have this on your in your note guide? Yeah. There you go, right? And then the speed, the escape velocity, then we just put in the speed of light squared. So this thing here is 3.00 times 10 to the 8th meters per second. That's the speed of light. That's a fundamental constant. This is the mass of the black hole, right? And then this is our 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. Now, here's the funny thing, is that you can calculate the Schwarzschild radius of any object. The moon has a Schwarzschild radius. The Earth has a Schwarzschild radius. Our sun has a Schwarzschild radius. It's just that all of those objects are bigger than their Schwarzschild radius. It lies somewhere inside them, and therefore all the mass, since it's not inside there, it isn't a black hole. But if a black hole is basically something like a neutron star, something that collapses so far that it collapses inside this point of no return, that all the mass is inside there, well, then it's pushed out of our universe. Basically, it's like that sheet of rubber. You've bent the sheet of rubber down, 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 and then it's separated, like a bubble, right? It's separated from the universe. This is a part of the universe. You can go to it, you can just never come back. Yeah? The point of no return. So, I think, do we have an example of this in your thing? There, put that in your notes, right? What is the maximum radius of a black hole that is 30 million times the mass of the sun? This would be a supergiant black hole. We think Andromeda has at least a 30 million stellar mass, solar mass, black hole in the center. So put this example in your notes. So that the Schwarzschild radius is going to be 2 times 6.67 e minus 11. And that's Newton meters squared per kilogram squared, right? Okay. The mass is 30 million, right? So 30 E6, right? 30 times 10 to the 6th times 1.99. Is it 1.99 times 10 to the 30th? There it is, right? Okay. I need to demarcate this. I'm going over into this thing. This is forbidden here. Look, I'm drawing a boundary. Now we're good. There's the example problem, right? And then we have to divide by the speed of light squared. So put 3 E8, there's 3.0 E8. Don't forget to square it. Right? This is meters per second squared. Newton is, by the way, a kilogram meter per second squared. I'm just trying to see what our units do here. This kilogram cancels that one. This one cancels that one. Meters squared and meters squared. And we need meters. We need a meter. Oh, there's the meter. That's the one that's left. Second squared goes away. Take your calculator. What do you get for the... So 2 times 6.67. Right, times 30 E6. So this is 30 million solar masses, right? Times 1.99 E30 divided by 3 E8. Do this. It's one of the few peppy things we're going to do. Do you guys get... I'm going to say 8.85 is what I'll say, times 10 to the 10th meters. So what this means is if you had 30 million solar masses, you would have an event horizon that is about, I think it ends up being, it's like more than half of an astronomical unit, right? So here's this thing. Here's this area of no return. If you ever went inside that, you could orbit inside that, okay? But you could never escape. You would never ever be able to get out because any point inside here you'd have to go faster than the speed of light to escape. So that's why it's called a black hole. Light itself, you could shine a flashlight and light itself would not have the velocity to escape from this black hole, right?